In the previous videos, we determined the depth distribution of the gold atoms in the three samples here. So we know now where the gold atoms are. We don't know how many gold atoms we have. So we don't know the concentration of the gold in the layers. So to determine the absolute concentration, we need to calibrate the spectrometer at the intensity scale of the spectrometer. And to do that, we use a reference spectrum. Normally, we just use a pure sample of the material we're looking at. So we can take gold 4D from pure gold in this case. Essentially, the idea is that you know what you have, so you can put in the start depth and end depth. You know the exact structure you have. So in this case, it's pure gold, so it goes from 0 to infinity. So I can put in 3 or 4 nines here. And sure enough, as you can see, it works very well. The background fits very nicely over the full range. You might, in some cases, have a small surface contamination. You can correct for that by putting in a start depth here. Let's try with a very thin layer. That's apparently not the case, but in some cases you would have that. You can easily correct for that. That's fine. You could also have not a pure sample, but say a thick sample. You could deposit a lot of material on top of a substrate, and then say if you have at least 100 angstroms, you can then put in, then you know you go from 0 to 100 angstrom. You can simply put in 100 here and do the analysis and find the, uh, the primary spectrum for that. Because the idea is now that with the Quasis analysis, well, I should mention that in some cases when you use the reference spectrum, you might not get exactly a fit here. So if you know that you have a pure sample, you may then allow yourself to correct a little bit here, but no more than about 5%. So if you need to go down to 0.89 or lower to make it fit here, or higher than about 1.01, then you know either that your sample is not homogeneous or something is wrong with your spectrometer. So the idea in Quasis analysis is always that you remove the effect of the transport in the sample. And by doing that, you end up with a spectrum from, in principle, from a single gold atom in this case. So this is always what you do. And therefore, you will always end up with the spectrum from a single atom. And this, of course, should be the same in all cases. So when you do analysis of an unknown sample, you should get the exact same intensity and shape as we have here. Shape may be slightly different if you have some chemical effects going on the low energy side, but the intensity must be the same. So we save this and overlay it with the spectra that we analyzed later on. So to save the green spectrum, I click Save here. You can put in comments, you can put in the file name. I just take the standard file name here. It will come up here now. Hit Save, and now it's up here. You see ANL for analyzed. So it's this one analyzed. So it's the FEV spectrum determined from there. Okay, so now to analyze the spectra, we take the first one here. We remember that was from 0 to about 15. We can use simplex here if we want to and do it like this. It was about 13.5. And now we want to determine the concentration in this layer. Maybe it's not pure gold everywhere. Maybe we form islands on the surface. It's very likely when you deposit one material on top of another that you form islands. This will show up with a smaller effective a smaller effective concentration in the layer. So to do that, we need to compare to this spectrum that we just determined here. That should be compared to this green one here. To do that, you change the plotted spectra here. Instead of having the output plus the input, output is this and input is that. Instead of having that, we would like to have the output plus a scaled reference. So I hit here, and now it tells me what to do. First, I should click OK, and then I should click the file where we have the reference spectrum. That's this one. So I do that, click OK, and then I click here, and then we have the two spectra on top of each other, and the fit is very good. What you see is that the scale factor is not 1 here. That means that one is scaled compared to the other by about 0.8. So that indicates that we have a concentration here of 80%. We can see that more clearly if we go to Ilan's passive substrate here. Choose that, and I can start with the full coverage, and then I can vary the height, and you clearly see that a height of about 13 is correct. And coverage 100. If I take full coverage, I get a scale factor of 0.8, same as we had before. So now I want to have the scale factor as 1, because then they are exactly the same. Go down here, 0.8. This gives me exactly the same intensity here. Because what the software does, it looks at the two spectra between these two lines. It takes the area, and this shows here the scale factor, the ratio of the two areas. So that's about 80%. And now it's 1 here. So this means this is the correct structure here. So we have islands formed on the surface with a height of about 13 angstroms and covering about 80% of the surface. We go back to this representation here. Concentration is 80%, or we have islands covering 80%. That's of course the same. So now we move to the second spectrum, number 2, and we find the structure. We could do that. Yes, we could do it. Maybe remember what we had, or we can also go to output plus input here and take the simplex. So we take the simplex algorithm, move out here, and see what we get. We hit background here, and we get about 10 to 40, 10 to 20 angstroms. And now again, we compare to the reference spectrum. We compare this also on an absolute scale. So to find the concentration of gold atoms in this layer. So to do that, I again change here the plotted spectrum to this mode here, out plus scale reference. It, it tells me what to do. I could hit this first and then that. But if I don't want to change the reference spectrum, I just hit cancel. We already loaded that, so I can just hit cancel. We have it already here. So now the fit is reasonably good. There's a small shift here. This could be a charging effect. You see that on insulating samples. You see a lot of charging many times. In this case, it's very small because it's gold. So I just use the E shift here. You can use that to compensate for that. That's here now. Now they are lined up. And what do we get? We get a scale factor of about 0.7. Now the fit could maybe be slightly better here if we change to something like this. So we now know that we have about 0.7. Concentration is about 0.7 in this layer. The gold is present from about 10 to 22 angstroms. Scale factor, or the concentration in this layer, is about 70%. So this means that on the islands that we had before, we have some nickel in between. Move to the third sample, and here we may remember what we had. We had about 25 to 35. So put in that here, and sure enough, we get a good fit here with the start and end death. And what we see now is that we have concentration of about 50%. About 50% from 26 to 36, 37, and the scale factor about 0.5. So we have a concentration of about 50% in this layer, going from about 25 to 36 angstroms in the sample.